Now it's 30.
And the ER now.
Good day. It's my pleasure to introduce Daniel Beltita from the Institute of Mathematics of the Romanian Academy of Sciences. It's a joint work. It's a joint talk with Fernand Pelletier from the University of Savoy, Mont Blanc. And the title of the talk is on the integrability of transitive algebroids. Please, you're welcome.
Thank you so much for this introduction and also for the overall opportunity to present here a few results that, as you said, I obtained jointly with Fernand Pelletier. In fact, the talk is based on a paper that is a preprint that is posted to archive in case somebody is interested in more details. The plan of the presentation will be the following one. Firstly, I will recall this problem of integrability of Lie algebroids, which is related to the fact that not every Lie algebroid arises from a Lie groupoid, so one has to do research in either of the two possible directions. So either one could try to find sufficient criteria for given Lie algebroid to arise from a Lie groupoid, or to enlarge the category of Lie groupoid in order to match all the Lie algebroids that exist. And it is to this second direction that this discussion will belong. So firstly, I plan to discuss this a bit. After that, to present the class of spaces that allow us to recover all the transitive Lie algebroids. So basically, we weakened the notion of classical notion of smooth manifold. We replace it by what Raymond Barre in 1973 called Q-manifolds. And in the end, I will explain how we can do that, how we can, that indeed this notion is suitable for recovering all the transitive Lie algebroids. The notion of groupoid is already well known, and I will actually recall it only in order to fix some notations that maybe are not widely used by other people. So I will denote the total space. So a groupoid is basically an associative multiplication on a set G. It is not defined for all pairs, but just for some of them. And there is a set of unit elements denoted here by M. An injective map from this set of objects into the set G, called the object inclusion map. As you probably already know, this terminology, objects and arrows, comes from the category theory, but I would like to spell out the whole definition in order to fix the notation. Every arrow has a target and a source that belong to this set of objects. And we pinpoint the set of composable pairs, namely pairs for which the source of the first is the target of the second. So we think of these arrows as pointing from right to left. And the multiplication map that is associative whenever it makes sense. And we also have that every arrow is invertible. So we basically change the orientation of an arrow, and if we compose this with the initial map, the initial arrow, we obtain an arrow like this, one subscript x, where x is a corresponding target or source, depending on the order of the composition. We use this notation with two parallel arrows for a groupoid, but we won't keep indicating T and S, and we just denote it by G goes to M. So this is only an algebraic structure. It can be rephrased very briefly that it is a small category whose arrows are invertible. And in order to do differential geometry, we consider the case when the set of arrows is a smooth manifold, so it is the set of objects. The target and source are submersions, smooth submersions, of course, and this object inclusion map and the multiplication map are smooth. This last condition makes sense because of the fact that as T and S are submersions, this set of composable pair is basically the pullback of the diagonal through a submersion, so it is a submanifold. So the domain of M is really a submanifold, and then it makes sense to speak about smoothness of M. And automatically, the inversion is smooth, and the image of the object inclusion map into G is a submanifold. For reasons that will become clear a little bit later, we do not identify M as with a subset of G, but we really keep in mind that there is a map that goes from M to G, is not just a set inclusion. So this is a Lie groupoid, and we will mostly concern with locally trivial Lie groupoids, namely the ones for which this map TS is a surjective submersion. So basically it means surjectivity of this means that for any two objects there is an arrow that goes from one of them to the other one, and moreover this is a submersion. The example that will be the model for our development, and it's a classical example, is the so-called gauge groupoid of a principal bundle. So the data is a principal bundle whose structural group is a Lie group G that acts on the right as usually, and the corresponding gauge groupoid is a groupoid whose set of arrows, whose arrows are exactly the G equivariant diffeomorphisms between the fibers of this bundle. So the fibers are the orbits of G, and we have, and they are of course smooth manifolds, and the G equivariant diffeomorphisms are the arrows of the groupoid. We denote by capital P subscript X the fiber of P over a point in the base. And the structural maps are pretty clear, namely the object inclusion map takes every point in the base to the identity map of the corresponding fiber. Target and source of such an arrow are, as expected, the target of gamma is P sub Y, source of gamma is P sub X. The multiplication map is just the composition of arrows whenever it makes sense. And the inversion is just the inversion of maps. This is the original description of the gauge groupoid that goes back to the work of Charles Ehresmann. But in order to organize it as a manifold, one would require it to be expressed as a quotient of P cross P over the action of G. But just in order to understand very clearly why it is a groupoid, it is this description is quite intuitive, I find it. And we will actually consider that its base is not as I wrote here, the set of all fibers, but rather the base of the groupoid of the principal bundle, because we have this natural identification. So this will be our main example of Lie groupoid that we want to construct in a wider framework. I mean, by weakening the notion of smooth manifold that is involved in all this picture. Lie algebroids, again, in order to fix the notation, are so a Lie algebroid will be a vector bundle Q from A to M, endowed with vector bundle homomorphism into the tangent bundle of M, for which we have this commutative diagram. And moreover, we have the following piece of structure, a Lie bracket on the space of sections of A, satisfying the following Leibniz identity. So when the bracket of X, so for every smooth function on the base, we can multiply a section with such a function. And the bracket of X with phi Y is the derivative of phi, but we cannot take the derivative of phi with respect to a section, and therefore we map the section through A to a tangent, to a vector field. So here we have a vector field, its action on the function multiplies y, and then is plus the function multiplies the bracket. Here and here is the Lie bracket that is an additional piece of structure on this vector bundle. A very important and also simple example of Lie algebroid is the tangent bundle itself, when the anchor map is the identity map. If we have this property that this condition satisfied, then the natural map from cross sections of A, smooth cross section, to vector fields given by the action of A is a Lie algebra morphism. And as it's written here, the map A is called an anchor, the anchor. And we say the algebroid is transitive if this is surjective. And it is with this class of algebroids that we are concerned with in this talk. As a basic example, I'd like to recall the construction of the Lie algebroid of a Lie groupoid. So for a Lie groupoid G with its base M, the Lie algebroid is constructed in the following way. Firstly, we look at the source map. The source goes from G to M. We look at the kernel of the tangent map to the source. This will be a sub-bundle of the tangent bundle of G, but it's a bundle over G. And here we have the object inclusion map, and we consider the pullback of this, or if we wish, the restriction of this bundle to the set of objects embedded into G. Because as I said, this is an embedding it's an embedded submanifold. So as vector bundles, the Lie algebroid of G is just the kind of vertical tangent bundle corresponding to the source map restricted to the set of objects. Exactly as in the case of a Lie group, where in order to define the Lie algebra, we take the tangent bundle everywhere, but we look only at the fiber at the unit element. Here we have a bunch of unit elements, and over that set we have a vector bundle, this one. And in order to, because we need also the anchor, we did this construction using only the source, but now we use the other map, the target. We restrict it to this, to a fiber of the source, and we take the tangent map, but only at the identity elements, because only they are involved here. And we get a map from here, this subscript X should be outside of the parentheses, from the fiber of the algebroid to the tangent space, exactly as we wish here. And the Lie bracket is defined following the pattern from Lie groups, namely, we extend the sections, cross sections of this bundle to the whole algebroid, to the whole groupoid, as a kind of invariant sections. And then we take the bracket as vector fields on G, and then it turns out that the bracket will be again invariant, so it comes from a section of the Lie algebroid. It's exactly the method of defining one of the methods of defining the Lie bracket on the Lie algebra of a Lie group. So we take two tangent vectors at the unit element, we build the corresponding right invariant vector fields, take the bracket, and then take again the value of the unit. So our main problem is will be to see which algebroids come from which transitively algebroids in this sense arise from a Lie group in this sense, and more exactly what to do when they do not come. But in order to show that the problem it's non-trivial, I'd like to briefly show an example of Lie algebroid that does not come from any Lie groupoid. So we will call a Lie algebroid integrable if it is isomorphic to the Lie algebroid of a certain Lie groupoid. And by the way, maybe I didn't mention so far, whenever I'll be talking about manifolds, I mean finite dimensional manifolds. So Lie groupoids will always be finite dimensional and so on. So this is what we mean by integrable algebroid, and I'd like to sketch the construction of a transitive algebroid that does not come from any Lie groupoid. The the first example was given by Almeida and Pierre Molyneux a long time ago, but this is a shorter example, an example that is easier to describe. Namely, the data are a closed two-form on a smooth manifold, and we consider the group of periods of that two-form. So it's integrals on singular cycles. And then we form a vector bundle like this. It's the Whitney sum of the tangent bundle with the trivial line bundle over M. This is a trivial line bundle over M. We take the direct sum with the Whitney sum with the tangent bundle. And this will be again another vector bundle on M. It has a natural projection onto the tangent bundle, and this will be the anchor. So, and this will be actually our candidate of the non-integrable algebroid. But we also need the bracket on its sections. An arbitrary section of this bundle is uniquely determined by a vector field and a smooth function. And so for two such pairs, we define a bracket that involves the two form here. So f and g are functions. And we take on the first component the usual bracket of vector fields. Here we have the action of a vector field on a function, the derivative of the function in the direction of that vector field. Here we have the other action, and we add this omega. If this omega would not be added, we obtain what is called the trivial Lie algebroid, namely and more generally, whenever we have the direct sum between a tangent bundle and a trivial bundle whose fiber is a Lie algebra, we can define a Lie bracket of on the corresponding space of functions. But anyway, in this case, for every closed two form, we have a Lie bracket on this, and actually a Lie algebroid on this trivial bundle. And the fact is that it is integrable if and only if the group of periods is closed, is a closed subgroup of the real line. And the closed subgroups look like this. In the opposite case, if it is not closed, then it is dense, as it is well known for the real line. So we don't, the corresponding algebroid is not integrable. And the question is how to extend the notion of Lie groupoid in order to exhibit this algebroid as still the Lie algebroid of some kind of differentiable or quasi-differentiable Lie groupoid. And this is what we are going to do next. In order to do that, I will describe, so an additional piece of explanation. So as I said, we need to generalize or to extend the class of Lie groupoids. But we want to stick to the algebraic structure of a groupoid. So the only thing we have to do is to weaken the notion of smooth manifold. So in some sense, we are looking for groupoid objects, not in the category of smooth manifolds, but in a wider category. And what I will show next is exactly what is this wider category that really allows us to recover all the transitive Lie algebroids. This so far mysterious category is consists of the so-called Q-manifolds, as Raymond Barre called them. And I will keep repeating for a while it is in the sense of Raymond Barre, because in a related area, the notion of the name of Q-manifold is shared by a different object, which is not what we mean here. So this Q actually is not any kind of mathematical object. It stands from the quotient. They are kind of quotients of smooth manifolds. For short, he called them Q variety. In order to define the structure, we need the notion of Q chart. So a Q chart of a set, we want to organize this set as a Q manifold. A Q chart is a mapping from a smooth manifold to this with the following two properties. Firstly, it is not injective, so our chart will not be injective. But if 2 points of the manifold are mapped to the same point in S, then there exists a local diffeomorphism between suitable neighborhoods of these 2 points, x and x prime. A diffeomorphism that is compatible with the quotient map in the sense that it maps fibers of pi to fibers of pi. And moreover, it takes those 2 points one to the other one. And it is the main difficulty in the study of this structure that local charts are not injective, so they are not invertible. And the second condition is that whenever we have two smooth maps from some smooth manifold into our M, with the property that they are taken down to the same map. In other words, for every point t in t, the values f of t and h of t are equivalent modulo pi. If the two maps are even equal at some point, then they are equal on a whole neighborhood of that point. The motivating or the motivating example for making this definition is just a general smooth manifold. Think of this of a smooth manifold with an atlas, fixed atlas. Then we have parameterizations from the open sets of the atlas onto suitable open sets of our manifold. And if we form the direct sum of these parameterizations, we obtain a map defined on the direct sum of all domains of parameterizations. And this map goes to the manifold. And it is not injective, but by the if 2 points belong to the same image of parameterization, then we have the well-known change of coordinates between the corresponding parameterizations. That change of coordinates is this diffeomorphism that takes the points one to the other one. So this is a kind of the manifold structure, or I mean, an atlas can be regarded as a Q chart with this special property where these two conditions are satisfied. But because not every Q chart comes from a manifold, we actually obtain a slight extension of the classical notion. I hope some example will show you what is going on. If the Q chart is an atlas, we call it a Q atlas. Two Q charts are called equivalent if their disjoint union is again a Q chart. So a Q chart meaning basically that we have these two conditions satisfied. In particular, the first condition really gives us some kind of compatibility between the two. And a Q-manifold is a set together with an equivalent class of Q-atlases. So the basic idea or the basic notion is that one of Q-chart is satisfying these two conditions. And so much about the objects of this category of Q-manifolds. The morphisms are defined by existence of smooth lifts. So a map between two Q manifold is Q smooth if it has if for every two, here is a mistake, for every 2 points S1 and S2, if we have f of S1 equal to some S2, then we have basically local charts in some sense around S1 and S2, and the smooth lift of our mapping. You see, if these local charts were injective, then we could say that this last equation is equivalent to the fact that f hat is pi 2 to the minus 1 composed with f composed with pi 1. But as pi 2 is not injective, we have to write it in this way. So we cannot say like f has a local in suitable charts, f has a local expression as a smooth map because we don't know what means local expression. We can only say that it has a smooth lift, and we have to do with that without injectivity of these local charts. And as a matter of fact, one can prove that if a Q-manifold has such an atlas, which is locally injective, then it is necessarily a smooth manifold. So the Q-manifolds which are not smooth manifolds will never have locally injective charts. There are always many points that are mapped to the same. But for instance, here we say that there exist points and not that for every point, because if we have this condition satisfied for some points that are mapped to S1 and S2, then we have this for every point. For instance, because of the first condition, we just compose with suitable diffeomorphisms to obtain this property for any point in the fiber of S1 and S2. Well, so now we have a category of Q-manifolds with these objects. It is pretty clear that a composition of two smooth maps is again Q smooth. And now we proceed to define the group objects in this category. So a Q group is a Q-manifold endowed with a group structure such that the corresponding structural maps are Q smooth. This was again introduced by Raymond Barre. And for us, some of the most important examples are actually the Q groups. The first example is that is the quotient of the additive real line by the subgroup of the rational numbers. I'd like to insist on this example because it shows that the topology, Q-manifold is an object that does not have a useful topology. For instance, in this case, the quotient topology is trivial. We can consider it, but it is trivial, and this creates the problem that, for instance, we could think of the notion of a vector bundle whose base is such a Q-manifold, but we cannot talk about local properties like local triviality, because we don't have open sets. So we have this is a problem to be dealt with when one would like to extend the facts from smooth manifolds to such Q-manifolds. And the more general class of examples is given by Lie groups with an immersed normal subgroup, in generally speaking, not closed subgroup. And then the quotient is always a Q group, and the quotient map is a Q submersion. And as I said, it's interesting, particularly in the case when N is not closed. Q submersion or Q other properties are defined by existence of lifts with the corresponding property. For instance, Q submersion means that pi has a lift that is a submersion, or equivalently for Q manifolds, one can define a natural notion of tangent space and tangent bundle without to say what means locally trivial bundle. And Q submersion means that the tangent map of pi is surjective, as in the usual differential geometry. So here we have Q submersion, above we have Q atlas. But in what conditions this Q submersion is really a Q atlas? It is if and only if this subgroup is pseudo-discrete. Meaning that if we have a smooth function from a smooth curve into G whose values are contained in N, then this is necessarily constant. For the real line, we have only this kind of examples, but I mean non-connected. But it turns out that assuming the continuum hypothesis, one can prove that there exist connected pseudo-discrete subgroups of Rn if in dimensions higher than 2. So there are many examples of Q groups, in particular Q manifolds that are not manifolds, are not smooth manifolds. This is the point of this slide. And now we will, with this notion at hand of Q group, we go on to define principal bundles or a suitable notion of principal bundles in this category. Our notion of Q principal bundle will be basically such a map from a Q manifold to a classical manifold, smooth manifold. Except that the structure group is Q, so is a Q group. So it's the same definition as in the case of smooth principal bundles, except that the total space and the structural group are Q manifolds. But the base must be smooth. We assume it to be smooth. And as usual, the fibers of this projection are the group orbits, and we have a local trivialization of the principal bundle. But here I would like to emphasize, here we speak about trivialization. It makes sense to speak about local trivialization because the base is a smooth manifold. If we insisted that the base to be a Q manifold, we would not be able to write such a diagram. But for our purposes, it's enough to consider to have a good notion of Q principal bundle over a smooth manifold. And now, for the people, probably not very few, who are familiar with the relation between transitive Lie algebroids and principal bundles, I hope the path is pretty clear. So we are going to develop a version of the Atiyah sequences for two principal bundles, and this should be enough to, I mean, in the end, we will prove that this is enough to recover all the transitive Lie algebroid. So given a Q principal bundle whose structural group is G, we do the following construction. On the one hand, we consider the tangent space of this Q manifold P. This is in turn a Q manifold acted on by G. We can consider the quotient, and we call this Atiyah of P, the quotient of the tangent bundle of P by the action of G. On the other side, we have the space of G orbits in P, which is the base on this smooth manifold. And here we complete by a suitable, by a map that exists and makes this diagram commutative. And we are going to eventually show that this bottom arrow is actually only algebroid. But please note that its base is a smooth manifold, is not a Q-manifold. It also has a natural map that could, a good candidate for an anchor map that takes a tangent vector to P. It is mapped to the base. And then we take it to the action, to the tangent of beta. So it, in any case, it is defined as required in order to play the role of an anchor. And we also have a natural map from P cross the Lie algebra of G by the action of G to this vector, to this so far just set via tangent map of P cross G. So here we just imitate the classical construction of the Atiyah sequence, and here we are stating the properties. I mean, it turns out that fortunately everything works for Q-manifolds, just as in the case of smooth manifolds. So for a Q-principal bundle, this set, as I announced before, is a smooth manifold, and the quotient map from TP to this is a Q submersion because TP is just a Q-manifold. Moreover, it is a smooth vector bundle, and we have such a short exact sequences of smooth vector bundles, and already I mean, okay, I wish to emphasize that I never talked about something like Q smooth vector bundles. The smooth vector bundles are just classic vector bundles in the classical sense, and eventually, or at last, we find that this vector bundle has the structure of a transitively algebroid, so its anchor is surjective as shown here. The conclusion is that for every Q-principal bundle, we have constructed a transitively algebroid. And the question is if we can reverse this process. To this end, we introduce this terminology that abstract Atiyah sequence is corresponds to a sequence of Lie algebroids. Actually, we regard the anchor map of a transitively algebroid. This is transitive, and its kernel is a Lie algebra bundle in the sense that it's a vector bundle whose fibers are Lie algebras. And we have a natural morphism, a notion of morphism between two abstract Atiyah sequences. Actually, there are two Lie algebroid morphisms that intertwine the corresponding maps. And the theorem that fortunately holds true is that every Atiyah sequence, or basically for every transitively algebroid, we can find some Q-principal bundle whose corresponding Atiyah sequence, or the construction of the previous slide, is just the given Atiyah sequence. So basically, every Lie algebroid arises from some Q-principal bundle, not from some smooth principal bundle, because there exists non-integrable Lie algebroid. But so far it is what we want. What we want to do next is to interpret this result as a result on Lie groupoids, because we basically want to integrate a Lie algebroid not to a principal bundle, but to a Lie groupoid, or to some kind of Q groupoid. And to this end, we will define what we mean by Q groupoid, and they should then to prove that they are enough to integrate the Lie algebroids. So the next, the topic of the next few slides will be the connection between Q principal bundles and locally trivial Q-groupoids. So in any case, we need some notion of Q-groupoid. A Q-groupoid will be a groupoid where the total space is a Q-manifold, the space of units is a smooth manifold, and then we have the usual requirements that the map, yes, here is some overlap between these two conditions. So the structural maps should be Q-smooth whenever they are defined, they involve some Q-manifold, and the source should also be a Q-submersion. And this implies by adapting some arguments from the Lie groupoids to the fact that it makes sense to talk about the domain of this, or in other words, the domain of this multiplication map is again a Q-manifold. So we have to develop a bit notion of transversality for Q-manifolds, but it's not difficult. And the Q-groupoid morphism will be, as one expects, a groupoid morphism that is a Q-smooth map. And then it's a base map as a composition of such Q-smooth maps. So the base map is a Q-smooth map, but a Q-smooth map between smooth manifolds is necessarily a smooth map. Here I'd like to draw your attention to a point that it's a bit delicate, is that unlike the case of Lie groupoids, the object inclusion map is a Q-immersion, but it is not an embedding in any natural way, as it was the case for the Lie groupoids. So here we cannot define, as I said, the Q charts are not injective. So the only reasonable way to define the notion of Q embedding would be to say that in some sense, inverse image through a local chart will be an embedding in the domain of the chart. Yes, so how we can prove this by the following example that is really a non-trivial one. So even in the case of Q groups, when the space of units is just one element, the singleton subset is an embedded submanifold if and only if this is a Lie group. So if we have a Q group which is not smooth, not a Lie group, then the singleton subsets, in particular the unit element, is not a submanifold in any reasonable way. It is just an injective Q immersion. So in particular, it does not make much sense to talk about something like the restriction of a bundle to a image to the space of units. We need to adapt with in a more careful way the notion of pullback actually. Okay, so this is what we mean by Q groupoid. The Lie algebroid of a Q groupoid can be defined just as in the case of Lie groupoids. So we take the fibers of the source, map the corresponding vertical bundle, and consider the pullback on the space of units. And the morphisms of Q groupoids give rise to maps between the corresponding Lie algebroids like this. So we have such a groupoid morphism. We consider its tangent map because, as I said, the construction of the tangent functor works well for Q manifolds. Then we consider the corresponding fibers of the source maps here and here, and the T phi leaves invariant, the corresponding, I will call them sub-bundles, but as I said, we cannot say that the tangent bundle of G is locally trivial, but let's call them bundles. And so we have this map, and now in order to construct the algebroids, we consider here the object inclusion maps from M to G, from N to H, and take the pullbacks of these vector bundles to the corresponding M and N. And here we have the algebroids of G and H. And now this diagram is completed by a map to the corresponding algebroids. And that map is a Lie algebroid morphism, at least if G and H are locally trivial. We are interested only in locally trivial groupoids because we are interested only to integrate, for the purposes of this talk, integrating only transitive algebroids. So for the category of locally trivial Q groupoids, we really have a Lie functor. So it makes sense to ask this question precisely. Is it true that every transitive Lie algebroid is the Lie algebroid of some locally trivial Q groupoid? And our main result is a positive answer to that question. And now we have the terminology that is needed in order to state one of the main theorems. It is like this. If we have a Q principal bundle, then the corresponding H groupoid is locally trivial Q groupoid. Moreover, we can construct an atlas that is at the same time a Q groupoid morphism. So this will be something that it's a main technical theorem that allows us to adapt the constructions from Lie groupoids, to extend them from Lie groupoids to Q groupoids. So this is the main point in the second statement. We can choose a Q atlas that is at the same time a groupoid morphism. And this will allow us to, in some sense, export some ideas or push some ideas from Lie groupoids to the corresponding Q groupoids. And secondly, every locally trivial Q groupoid is the gauge groupoid of a Q principal bundle. Again, a statement that two statements, the first statement in the first theorem and this one are well known for Lie groupoids, but we need them for Q groupoids in order to be able to relate the Atiyah bundles to, Atiyah sequences of Lie algebroid, transitive Lie algebroids to groupoids. And I will soon finish. These two theorems are useful in as much as if we are able to compute the Lie algebroid of a gauge groupoid. In the classical case, this is done by the so-called Ehresmann isomorphism. So the Ehresmann isomorphism for a smooth principal bundle gives us a Lie algebroid isomorphism from the Lie algebroid of the gauge groupoid to a certain to the Atiyah algebroid. So it relates to constructions. Basically from a principal bundle we construct two algebroids. One of them directly, which is the Atiyah algebroid. Another one that passes through the gauge groupoid, and the Ehresmann isomorphism is a natural isomorphism between these two. And the construction of this, that I will pass over it a bit quickly because it is actually a classical fact that requires just the quotient map given by the diagonal map and diagonal action of G on the principal bundle. We take the partial derivative and we compose with the inclusion of TP via 0 on the second variable, basically. And we thus obtain the decomposition upstairs is a fiber-wise isomorphism, but onto the Lie algebroid, but it is, only fiber-wise in the sense that the base it is not bijective. But using the fact that we have this, for this quotient map, we clearly have this property with respect to the group action. we obtain a factorization of this fiber-wise isomorphism to a true isomorphism of Lie algebroids. So in any case, this is the classical construction of the Ehresmann isomorphism, a construction that does not make, directly cannot be carried out for Q groupoids, because as you can see, it requires some bundles whose base would be a Q manifold. And as I said, we do not know very well how to work with such bundles. And then the idea is to use the previous theorems and that atlas groupoid to actually push this classical isomorphism to the Q setting of Q bundles. And the result is the following one, and I will finish very soon. We introduced some notation for the categories. We worked with principal bundles, transitive algebroids, and locally trivial Q groupoids. And we have these functors from principal bundles to Lie groupoids, from principal bundle to Lie algebroids, and here the Lie functor. And the Ehresmann isomorphism gives us a connection between these two. In the case of smooth groupoids, it turns out that we can prove the same for Q principal bundles, namely this composition of functors and this one are isomorphic, in the sense that not only for every object here we obtain an isomorphism of the corresponding values of the functors, but also for any morphism between the corresponding objects, we obtain a morphism between the corresponding values of the functors. So, in other words, we have natural isomorphisms or an isomorphism of functors, which is, good thing to good information to have in order to address the integration of general transitive Lie algebroids. And we have this corollary whose proof is just a summary of what the result we proved previously. So we start with an arbitrarily transitive Lie algebroid with this anchor. And firstly, we integrate it to an abstract or to a principal Q groupoid. Then we pass from the Q groupoid to its corresponding gauge groupoid. And because of the Ehresmann isomorphism, the transitive Lie algebroid we started from is the Lie algebroid of this Q groupoid. And this proves the corollary. Okay, I will stop here. Thank you so much for your patience.
Thank you. May I ask the first question? You had the first example where there is a central extension by a tangent Lie algebroid by use a closed-to form. Can you illustrate your procedure on this very simple example? So you say that you can always integrate it to a transitive Q groupoid, right? Or you call it locally trivial.
You mean to specialize the construction?
Yeah. How it works? Is it easy to see by use of the periods or what? I don't know.
In fact, that appeared here and there in the literature. Maybe the first paper, sorry, the first paper I know about is by this, no, sorry. This you mean.
Right.
So if this group of periods is not discrete,
yes,
we still obtain this Lie algebroid. We
yes.
have this Lie algebroid. The fact is that then what we have to work with is the quotient of the real line by that non-discrete subgroup.
Okay.
Which will be a dense subgroup, like not like the rational numbers, but as for instance the combinations with integer coefficients of an irrational number, numbers of the form m plus n times r, where r is some irrational number.
Okay.
This is again a dense subgroup in the real line if the number is irrational. The quotient is the so-called irrational torus. And here and there, this appeared in the literature. The earliest reference I know is perhaps a paper by Tuiman and Vigering. So people who worked in geometric pre-quantization thought how to integrate what is not
Right.
integrable or how to.
So the group will be not as S1, but not S1.
No,
It
will be this kind of
this
torus,
kind
but
of
not.
Q. Is it an example of a Q group in your sense?
Yes, it is because every quotient of a Lie group by a countable subgroup is. But people also consider basically this as a kind of diffeological group. There is a notion of diffeology that is wider. But the advantage of this approach would be that this category of Q-manifolds is much smaller than the diffeological category.
Right.
So it's better to stay as close as possible to the
So
classical.
sufficiently small extension of the smooth category, right? So
Yes, I'm not sure if this is minimal, but that would be a nice question, but I don't know if it is minimal or not. But
right.
it's certainly smaller. Yes.
Smaller than diffeological, right? Okay, let me ask others if there are other questions.
So you say that there are no possibility, that's a very, is to extend to diffeological category is a kind of the, you need more restriction, right? Yes, you cannot check here. So that you say that the Q-manifold is a more or less right category for extension and not diffeological. Yeah.
Yes, I think it's, I mean, not I think, it is certainly smaller in the sense that there is an embedding functor which is not surjective. Yes.
Do you have any idea if it's possible to extend this to the more general problem of integration of Lie algebroids? Because I think the problem is kind of similar in even for a non-transitive one, right? So
yes,
have
it
the
is
problem
true.
with monodromy, yeah.
Yes, in fact, we are thinking in that direction. In the classical, I mean, there are maybe two approaches that I know about to integrating Lie algebroids. This one is due to Mackenzie and basically uses this formalism of Atiyah sequences and so on. The other one due to Krajnik and Fernandez for characterizing the integrable Lie algebroids using those monodromy groups. Yes, but here we construct the groupoid, the candidate of a groupoid as a gauge groupoid, as I said. They construct that so-called Weinstein groupoid, which is a quotient of of a certain Banach or a topological groupoid by an equivalence relation. And
yeah, but it's a quotient of something infinite dimensional, but something infinite dimensional, right? Maybe it's not that
yes,
good.
but the result is finite dimensional. Yes, it's true. So that construction is different. No, it's a nice question. We are thinking in that direction, but it's not this approach. This actually, I thought this could be maybe suitable for your seminar because this approach of Mackenzie requires the construction of a principal bundle, let's say in terms of the Czech cohomology, and because your seminar is about cohomology, I thought to present. But the other one is not so cohomological one, not in this sense, not in the Czech sense, in Czech cohomology. Yes, it's a great question, but it remains to be investigated in the future.
I see. Okay, other questions? Okay, if there are no more questions, let us thank the speaker again.